This is AP Precalculus. We're doing the review for the AP exam. This is the 3-peat-N activity. Make sure that you're doing this entire worksheet in under 6 minutes. And number one, we have this g of x function, which is to the power of 6. Oh boy. And we need to expand it, and we're looking for the term containing x to the power of 4. So it's important to note we don't need to do the full expansion, only the partial expansion with this x to the power of 4. So while I can solve this problem a little bit quickly, I want to explain how to do this problem a little bit more in depth. So this comes from a binomial expansion using the shortcut of Pascal's triangle. You'll remember the Pascal's triangle has this feature. It goes 1, 1, 1, 1, 2, 1, where when I add 1 and 1, I get 2. And then all the sides are always 1. And then in order to find the inside, you add 1 and 2 to get 3. Oop, in pen though. And you add 2 and 1 to get 3. And then you do the same thing. You start with the 1s, and then I add the 1 and the 3 to get 6. 1 and 3 is 6. 1 and 3 is 4, 3 and 1 is 4, and then 3 and 3 is 6. And then you keep adding on. Notice I had 2 numbers, then I had 3 numbers, then I had 4 numbers. This pattern continues on and on. And what row do we stop at? We stop at the row that starts with a 6 for the second number. So I'm on the 4th row now. This is the 0th row. So I'm going to go 1, 5, 10, 10, 5, 1, and then finally 1, 6, 15, 26, 15, 6, and 1. There's always symmetry to this. That's how I knew I messed up. Symmetry over this center line, meaning there should be either a double, or sometimes the middle just has a single number, right? Okay, so I have this row, which is the one that corresponds to the power of 6, and I can write that out a little bit more. I can say 1, then 6, then 15, then 20, then 15, then 6, and then 1. From here, I know that I always descend powers for my x. It starts with x to the power of 6 in my first term, so it goes x to the power of 6, then x to the power of 5, then x to the power of 4, x to the power of 3, x to the power of 2, x to the power of 1, and then nothing. You'll notice I didn't need to write all these out. Really, I just want this one right here, this 15x to the power of 4. And then the other way works as well. So when I'm looking at the 3, I'm going to start over here on the right-hand side and say this is times 3 to the power of, and again, you go all the way up to the power of 6. So 3 to the power of 6 times 3 to the power of 5 times 3 to the power of 4 times 3 to the power of, that's supposed to be a 3, times 3 to the power of 2, times 3 to the power of 1, and then times nothing. So the term we're looking for is the one that has an x to the power of 4. This one has an x to the power of 4. Notice it has a 15 and a 3 squared, so 15 and 3 squared is going to be C. In number 2, we have a equation where we're trying to solve this. All right, so we're just going to set this equation equal to this equation. So here we go. We're going to say log base 2 of x plus 3 minus log base 2 of 2 is equal to the other equation, which is just 2. So whenever you have 2 logarithms on one side, you want to combine them into a single logarithm using logarithmic properties. Because I am subtracting the outsides, I will divide the insides, and this is going to be still log base 2. The insides are now x plus 3 for the numerator and 2 for the denominator. That's still equal to 2 on the right-hand side. Now I need to get rid of this logarithm. The only way you can do that is called exponentiation. Essentially, you take the same base that you have down here, and you say that is the new base. It's base 2 and a base of 2, and really what I have here, let me move you down. I have this new equation that says 2 to the power of all of this is equal to 2 to the power of all of this. And when you do that, this 2 and this natural log of base 2 are going to cancel out. So cross, cross, cross. And you're left with just x plus 3 over 2 is equal to this 2 to the power of 2, which is just 4. And then from here, you can cross multiply and solve. So I can say 2 times 4 is 8. And cross multiplying the other direction, there is nothing down here. It's technically over 1. So 1 times x plus 3 is just x plus 3. And then I can solve by subtracting 3 on both sides, and x is equal to 5. Be careful here. If you immediately choose this, you could be wrong, because the one last check that you always need to do whenever you have logarithms and logarithmic properties with equations is you want to plug this back in and make sure that it makes sense. If I plug x back in and say 5 plus 3, okay, this inside this argument was positive. I can't plug it in there or anywhere else. As long as all the insides are good, then you have an answer. Sometimes you'll have 2 answers, like negative, like if I had the answer -4 and 5, when I plug in -4, this made up answer, a -4 would not work because -4 would make the inside negative, and I would have to eliminate that as an answer. Luckily, the only answer that we had also ended up working, so 5 is indeed the correct answer. Sometimes you'll get this answer, there are no values in the domain of f if this somehow was plugged into my argument and I had a negative answer. All right, in number 3, we're just trying to match 2 tangent of x with a graph down here. You might remember that tangent of x in general looks like this, where it comes up kind of like our x cubed function. and it repeats over and over again. I'm noticing that all these functions are kind of zoomed in a little bit too much. I'm noticing that we have a cosecant. This is actually a secant function and a cosecant function. Neither of those are going to be useful to us because they're not even close to tangent. It's really between a and b, and you have to remember that with a positive tangent starts in the bottom left and goes to the top right. It's very similar to that right-hand rule where with a polynomial, the sign up here talks about the right-hand behavior. If this is a positive, then the right side is also positive. And you can see that this is trying to do that. They just cut off the tips of our tangent function. They zoomed in too far. So the correct answer here is A. Notice that option B would have been correct if I had a -2 tangent because it flips it upside down where this comes down, this comes up, and you'd have this function that looks like this, which looks like option B. All right, that does conclude our 3-peat n activity. Thanks for watching.